final part under sounds. What we are learning here is under waves. There are three major parts: simple harmonic motion, then a general part about sounds or waves, and then a small part about sounds, and then you have light. So around 4 parts are there: simple harmonic motion, then a general discussion about waves, different types of waves, and then we discuss a little bit extra about sound, and then we will be learning about light. So under sound, the final part is Doppler's effect. Okay, so we are almost nearing the end of the midway. We are almost reaching the midway of this unit. Doppler's effect. There is Doppler's effect for sound, which is the most important thing, and there is Doppler's effect for light as well. We will discuss about that also under this, so that it will be complete. Right, let's start. Now, what is Doppler's effect? Let me first explain that with a elaborate that with a diagram. So imagine there is a sound source. Okay, there is a sound source. What are sound sources? Examples: a bell, a siren. Okay, something like that. So when the sound source is on, let's say you are looking at the sound source from top, from a drone or from a satellite, something like that. Then what will happen? From the sound source, the sound waves will be created like this, right? Sound waves will spread evenly everywhere, up, down, right, left, everywhere. The sound waves will be distributed evenly. Okay, so you have to draw this in equal gaps. I hope you understood that. Good, fine. Now you can see, let's say there are two, this is the sound source. I'll just mark S in the middle, that is the sound source. And let's say there are two observers here. One observer is here and the other observer is here. And we have discussed, when you have these circular wave fronts, the length between two circles will give us the lambda value, lambda. So here also length between two circles will give you lambda. Okay. Now in this case, both the observers and the source, now I'll just put O here for the observer. Okay, this is an observer, this is an observer, two observers are there. So when the observer and the source are at rest, the frequency of sound heard by the observer will be equal to the frequency of the source itself, because you can see the same wavelength is reached to the it reaches the person here. Okay, I hope you understood that. The sound is produced from the source, and that sound will travel to the person here, the observer. So the observer will hear a sound, and that sound that observer hears and the original frequency of this sound will be equal. Okay, right. So rather than saying that these two are at rest, we can say there is no relative motion. No relative motion. What is the meaning of no relative motion? One is both are at rest. If not, both are moving at constant velocity. You have to be careful. If they say constant speed, it's wrong. Why? If it is going this side at 10 meters per second, and if this person is going this side 10 meters per second, there is a relative motion. That's wrong. So it's either both are at rest, if not, both are at same velocity, moving at same velocity. What is the meaning of same velocity? If this is going 10 meters per second to the right, this person is also moving 10 meters per second to the right. So there is no relative motion. If there is no relative motion, the frequency of the sound heard by the observer will be equal to the frequency of the source. But if there is relative motion, now let's imagine the observers are at rest. Now this sound source is moving to the right. Okay. When the sound source is moving to the right, I will mark that initially. First of all, let's say the sound source now, it is moving to the right. Then what happens is the waves created will get a little altered like this. Well, something like this is going to happen. Now what I have done is, it's the same diagram. I have moved all the circles to the right a little, because this sound source is moving now to the right. Now imagine there is an observer here and there is an observer here. Okay. Now each observer will be experiencing two different wavelengths of sound. Now this wavelength I will take it as a lambda 1, and this person is going to observe a wavelength, and that is lambda 2. Okay, lambda 2. Right. Now if you draw the diagrams correctly, with the proper gap, you will see that lambda 1 is less than lambda. What is lambda? The original wavelength of the sound produced by the source. Okay. At the meantime, lambda 2 will be greater than lambda. Lambda 2 will be greater than lambda. So there's an issue there. This is what Doppler's effect is going to be. That is what Doppler's effect is all about. Now I'm going to mark certain important things. Now let's say here the frequency of the source is f naught. I will mark it here. F naught in this case is frequency of source. Alright. Let's say the frequency heard by this observer is f. Here also the frequency of the sound heard by this observer is f. Here the frequency of the sound heard by this observer is going to be f1, and here the frequency f2 will come. We'll take it like that. Okay. Now from the diagram itself we have figured out that wavelengths are different. This is a smaller gap, this is a larger gap compared to this gap, right? So lambda 1 is smaller than lambda, the original one, and lambda 2 is larger than the lambda, the original one. And when you compare the frequency, it will be the opposite. f1, f2, it will be this way, because the speed of sound in AR will be same here, because the source is moving, but the observer is not moving. Hence, the frequency will be the opposite. When this wavelength reduces, frequency is high now. So this person will hear a sound at a greater frequency than this the original frequency of this source. Now let's say the source is moving, but the sound it creates has a let's say frequency of 100 hertz. Then this person will hear a frequency greater than 100 hertz, and this person will hear a frequency less than 100 hertz. For example, 120, 80, maybe something like that. This. Okay, fine. So sometimes they will give diagrams like this, and they will ask you to find these lambda values. What is this lambda? What is this lambda? Something like that. So you can understand that lambda 1 is smaller than lambda 2. Okay. So what is going to happen there? Now I will compare this with this. Okay, all three. Let's compare. I have f and lambda, f2 and lambda 2, f1 and lambda 1. So to get the comparison right, I will use a letter C. That will be the speed of sound in air. Okay, speed of sound in air. Right. Now for the first case, if you see, there is a frequency, there is a lambda, and nothing is moving. Observer is not moving, source is also not moving. So here we can directly say, for the first case, this case, I can say C is equal to f lambda. Done. From that I can say lambda is equal to C over f. For this case. Okay, fine. And now for this case, if you consider, for this case, lambda 1 is smaller, lambda 2 is larger. So for lambda 1, the equation is going to be lambda 1 equals, it is smaller now, that is going to be, I think I made a mistake here, lambda is going to be equal to C over f naught, no, C over f naught actually, yeah, C over f naught, yeah. Here we have taken the frequency of this as f naught, so f naught, yeah. And frequency of this person heard is also equal to f now. Here f is equal to f naught, because that person is not moving now. There is no relative motion. That means the frequency of the sound heard by the observer and the frequency of the source are equal, right? Good. Now for this case, if you consider lambda 1, it will be C minus V over f naught. That will be lambda 1. Okay, what is happening there? V is the speed of the source. V is speed of source, speed of sound source. Alright, and then lambda 2, we can write it is larger, right? Lambda 2 value is larger, so it's C plus V over f naught. Okay, so from this you can understand that the wavelengths reaching the observers when the source is moving are different. This is what you call Doppler's effect. I gave you a small introduction. For Doppler's effect, we have different equations. For you to understand why Doppler's effect is taking place, I just wanted to introduce this part to you. These kind of questions are a bit rare, but recently I saw a question, they had given a diagram like this, and they had given these lengths, and then they were asking to find something. So here C minus V, V is the speed of the source, here C plus V. Why did I write like this? Because lambda 1 is smaller. Yeah, lambda 2 is larger, so something has changed. That's why this. Next, we are going to learn the proper equation, the common equation we use for Doppler's effect, and what is actually Doppler's effect, how do we define Doppler's effect, and all those things. We discussed why Doppler's effect actually takes place when there is a relative motion between the source and the observer. There is a change in the original wavelength, there is a change in the wavelength sensed by the observer. Okay, the original wavelength of this source was lambda, but the sound heard by this observer will not have the same wavelength, it will be different. Same with this person also, right? That is what Doppler's effect is. So if you want me to put that into a statement, why is this statement important? Because normally if you get Doppler's effect for essay question, most probably the first question will be state Doppler's effect. So this is what you have to mention there. When there is a relative motion between the sound source and the observer, the frequency of sound sensed by the observer, we call it apparent frequency, there is a name for that, will be different from the original frequency of the sound source. This phenomenon is called Doppler's effect. Imagine there is a sound source, it is emitting a sound of 100 hertz. If I am just staying at rest and the sound source is also at rest, I will hear a sound and that sound will have a frequency of 100. But if there is a relative motion between me and the sound source, then I will hear a sound, but that sound will not have a frequency of 100 hertz. It might be greater than 100, it might be less than 100, depending on how the relative motion is, like this. Okay, right. So this is the definition. Now let's move on to the this is the qualitative part. Let's move on to the quantitative part, the equation and all those things. This is the equation for the apparent frequency. All right. What is the apparent frequency? The frequency heard by the observer when there is a relative motion between the observer and the sound source. That is what apparent frequency is, and the apparent frequency will be equal to the speed of sound with respect to observer divided by speed of sound with respect to source, and you multiply that by the frequency of the source. Okay, this is the equation, and it looks very large and bit complex. Let's make it very simple. For apparent frequency, we normally use the notation F. For speed of sound with respect to observer, I will write an equation like this, that is C plus or minus VO divided by, below I will put C plus or minus Vs into F naught. I want you to remember this equation. The entire Doppler's effect of sound revolves around this single equation. If you can remember this equation, you can manage any question. All right. So I have introduced certain terms here. Let me quickly write down those terms. Now F is apparent frequency. We don't have to worry too much about it. This is F, okay, apparent frequency, and F naught is the original frequency of the source. F naught, that 100 hertz I was talking about earlier, something like that. And then I have C, VO, C, Vs. Now earlier also we discussed about C. C is the speed of sound in air. In normal atmospheric conditions, speed of sound in air will vary from 330 to 340. In some questions, it's 320, 330, 340. That is the range for speed of sound in air. So if you are getting an answer like 1000 meters per second, if not 800 meters per second, 2000 meters per second for speed of sound in air, that means that's definitely wrong. It should be from 330 to 350 under normal atmospheric conditions. All right, fine. That is this C. So C is the speed of sound in air. VO is the speed of the observer. Okay, and Vs is the speed of the sound source. Now this is the definition for all those components. All right. Now you can see that I have put plus or minus here, plus or minus here. So this is just a common equation, not one equation, because you can't have both plus or minus here. Right. So there are few cases. There are around for around 8 cases. For each case, we have to figure out what these equations are. All right. Before we go to those cases now, C is speed of sound in air. It can't be 0. It will have a value because sound is going to travel in air at a certain speed. That speed can't be 0. But the observer speed, it can be 0 or it can have a value, because if the observer is at rest, VO is 0. If the source is at rest, Vs is 0. All right, fine. And then there is this plus and then there is minus. Now earlier we discussed, look at this diagram, when the source is moving towards the observer, if the observer is moving towards the source, the frequency will be high, and the wavelength, frequency will be high. And at the meantime, if the source is moving away from the observer, the frequency will be less. Based on that, here you can decide something like this. If you want this F to be high, the numerator must be high and the denominator must be low. Correct? Good. When will we have higher F? Observer moving towards, source also moving towards, then only we will hear a higher frequency. So if your if you want f to be large, the upper part has to be large and the bottom part has to be small. All right. So when you consider all those things, let me do a summary here and see if you can understand what I have done there. Well, this is a summary, people. If observer is at rest, this part becomes 0. If source is at rest, Vs becomes 0. If the observer is moving towards the source, here you have to use C plus Vo. And if the source is moving towards the observer, here between this plus and minus, you have to choose minus. When this part becomes small, this becomes large. And when someone is moving towards someone, definitely frequency has to be higher now. So this. And the other one, if observer moves away from source, if the observer is moving away from the source, the frequency, apparent frequency should reduce. So minus on top, C minus V naught, and the other one C plus Vs at the bottom. So if you know these summaries properly, this equation and these things, these two are quite basic, not that complicated. This one, if you can remember one set of this, one set, then the other one is going to be the opposite of that. Then you can figure out for the equations. You will be able to alter this equation for all those cases I was talking about, right? Fine. So let's quickly analyze what those cases are. So the first case is when the observer is at rest and the source is moving towards observer. Now for this situation, I will just quickly draw the diagram. The observer is at rest. So the observer, I'll draw man, the observer, and if the observer is at rest, VO is 0, correct? And the observer is going to hear the apparent frequency. And the source, whatever the source it is, it will be here. I'll put S, and the source is moving towards the observer. So the source is moving towards the observer, and the frequency of the source is F0. Okay, I have put this word into a diagram, right? At that time, the equation for F is going to be this. So F is going to be equal to VO is 0, so only C will be there at top, down. Source is moving towards the observer, so it's going to be C minus Vs. This C minus Vs multiplied by FO. This is going to be the equation. All right. And how about the other one? Opposite of this one. The observer is at rest and the observer will be hearing an apparent frequency, and this time the source is emitting a sound of frequency F0 and the source is moving away from the observer. Okay. So the sound emitted by the source is having a frequency of F0. Here also the source is emitting a sound, but the person is not going to hear F0. The apparent frequency this time is going to be F equals C, only C up, C plus Vs into F0. I hope you understood this, because C plus, if the observer is going away, this plus down, and the source is going away, so plus down, observer is at rest, so only this part, right? So you don't have to by heart these equations, you just remember this, and based on the situations, you just can apply this, okay? So likewise, there are 6 more cases, and for each case, you should be able to figure out this equation, and let's quickly do that. Alright, these are the other 6 cases, altogether 8. So this one, when observer moving towards the source and source is at rest. Observer moving towards the source, source is at rest, Vs is 0, and source will be emitting a sound of frequency F0, and the observer will be hearing that sound at an apparent frequency of F. Alright, that. And here, likewise, I will complete all the diagrams and then see if you can understand. I just drew all the other remaining cases. Let's try to fill the equations. Let's try to write the equation. Now for this, how is going to be the equation? Apparent frequency F is equal to C. Observer is moving towards, so it should be C plus VO. C plus VO divided by just C, because Vs is 0 into FO. Okay, right. I'm using this as my guidance. I hope you can remember this. I'm using this as my guidance. So let's use this here. Right, here the equation for apparent frequency is observer is moving away, so it should be C minus VO. C minus VO divided by C into FO. Okay. Now what you can do is before in this you can pause this video when I had when I was displaying only the 6 cases. Then you can fill the blanks, and then maybe you can go back and check. Check other answers afterwards. I don't know. You can do it. Now I have spoiled the fun. I have already written for 2. Maybe for the other 4 you can try. Now before I write these 4 equations, you can fill it and check whether your answers are correct. If you take this one, both the observer and the source are moving towards each other. Okay, that means it's going to be C plus VO, at the bottom C minus Vs into F naught. This is when they will hear this is when the apparent frequency will be maximum. Both are moving towards each other, so maximum. All right, here F is going to be what? Minimum, because both are moving away from each other. So that will cause the apparent frequency to drop a lot. Okay, fine. Now this is a bit different. Here the source, the observer is moving towards the source, but the source is moving away from the observer. But to consider Doppler's effect for this case, it's very important that these two speeds are not equal. If these two speeds are equal, there is no relative motion between these two, then you can't, there is no point of writing an equation. Okay, then what will be the equation? F is equal to C plus VO, because observer is moving towards, and down also C plus Vs, because source is moving away, into F naught. We did not come across an equation like this. And here F equals observer is moving away, so C minus VO. Source is moving towards, then down also C minus Vs into F naught. So these are the 8 equations, 1, 2, 3, 4, 5, 6, and the earlier 2 we discussed. All right. So it's like honestly there's one equation, depending on the situation you just have to adjust and get these numbers. All right. For Doppler's effect, this is the basic theory part, but the questions are not very easy as you think it is. Questions are a bit complex, so we will have to learn different cases. There are different cases when it comes to Doppler's effect. Perhaps we have to discuss all of them separately, then only you will be able to do questions. In real life, where do we see Doppler's effect? Now imagine this case. Now take this case. No, wait, take this case. Okay, take this case. This is a case where a speed gun is used. What is a speed gun? These traffic policemen have a gun kind instrument in their hand. They use that gun to find the speed of vehicles, and then they can find they can find out whether the vehicle has breached the speed limit. Okay, so what they do is imagine the S is the source, the speed gun. So this is like the policeman's hand. Speed gun is on policeman's hand. So what happens is the policeman will send a sound wave from his gun, or maybe an ultrasound wave from his gun. So a sound wave will be released. So the sound wave will go, and there's a vehicle moving like this, no? So it will strike the vehicle and it will reach the gun again. Okay, so if the frequency released from the gun is 1000 Hz, for example, the frequency received back by the gun will be greater than 1000 Hz. There is a difference in frequency. Then Doppler's effect, we can apply Doppler's effect for that, and then we can find out the speed of the observer, speed of the car. Okay, so that is a little different. You can't use these equations for that. I will explain that little later. There we are using a reflected sound. You send a sound to the vehicle, it strikes the vehicle and it comes back to your gun. That is reflected sound. So that is also Doppler's effect, but you can't use these equations for that. In that case, we have to do 2 steps. My point is, Doppler's effect is considered in speed guns, and also sometimes you use these scanners to detect these clots inside our blood vessels. There also we use the concept of Doppler's effect. Okay, so those are some real life examples for Doppler's effect. We were discussing about the speed gun, the policemen carry their hand, and yeah, why don't we just discuss how Doppler's effect is involved there. So this is Doppler's effect for reflected sound waves. It's not just for that speed gun scenario. This is the common, we are going to derive a common equation for whenever a sound is reflected. Okay, I'll take that as the example. Let's say there's a policeman and he has a speed gun, and there's a vehicle approaching the policeman. So the policeman in his hand has the speed gun. So the speed gun is the source. Remember that speed gun is the source, and there is this vehicle moving towards the policeman. Correct? Normally that's how it happens, right? So I'll take this speed as v, and the policeman's target is finding this v. Do you agree with me? Yes. Good. Now this is going to be the case. Now when the policeman shoots the sound waves will travel from this. These green color ones are the sound waves traveling. Okay. So for this instance, the policeman is going to be, or the policeman's the speed gun in policeman's hand, it becomes the source, and the van or the vehicle, whatever the vehicle here, becomes the observer for this case. Okay, in this situation, because there is no sound here, just the vehicle is moving, and this sound is our concerned sound. So this becomes the source, this becomes the observer. All right. So that means if this is the observer, speed of the observer is v, correct? And what is the speed of the source? 0. And the frequency of this, let's take it as f naught. So yeah, f naught, and the frequency here, which is the apparent frequency, this is the observer now, that will be f. Okay. Now we can write an equation for this f. What is that going to be? F equals, the observer is moving towards the source, so I can say c plus vo divided by c, source is at rest now, c into f naught. So if you modify it a little, yes, we'll take this, okay, I have taken this as f naught, now I'll take this as f, okay, never mind, f. So from that I can say f is equal to actually c plus v over c into f naught. That is the first equation. All right, fine. We are not done yet. F is this frequency sensed by this moving vehicle, frequency of this wave sensed by the moving vehicle. V is the speed of the moving vehicle. That is what the policeman needs to find out. Good. After that, this sound wave will strike this vehicle and it will reflect back to the speed gun. It will bounce back. Now for that case, now you have to be a little careful. The speed gun, I'll just mark the speed gun like this. Okay, speed gun. And now we are going to consider the waves bouncing back from the vehicle. So if not, we can say reflected sound, that is a reflected sound, right? Now if the sound is getting reflected from this, now this actually becomes the source. Okay, and it is, don't forget, it is that vehicle, it's moving at a speed of v, it's moving at a speed of v, don't forget that. Okay, right. Now what happened earlier, the sound waves were released from the speed gun, it came up to the vehicle, and now from the vehicle the wave is reflected, right? And these reflected waves will be received by the speed gun. Okay, I'll just put speed gun SG, speed gun is the source, right, SG. Now the speed gun will receive a new frequency of sound. I will take that as a f dash, and the speed gun now becomes the observer. I hope you understood that. Okay, these waves will be received by the speed gun. So the speed gun will be the observer. The interesting part is, speed gun now, around the speed gun there will be two sound waves. One is, one has a frequency of f naught, the other one has a frequency of f dash. So they will be definitely different, and f dash will be greater than f naught. You will understand that, definitely greater than f naught. Why? It is reflecting back from this, and it will be greater. So there will be a difference in these two frequencies, so beats will be created. Based on that beat frequency, the speed gun will calculate the speed and it will give us the value. So how does it happen? Let's see. Now this equation was applied for this case now, right? For this case, let's apply the equation, right? Now okay, careful. Who is going to be sensing the frequency? The observer, and the observer is at rest now, because this becomes the observer, and the source is moving towards the observer. This is our Vs. All right, fine. So the equation for the new apparent frequency f dash is going to be speed of sound in air over speed of sound in air minus Vs into f naught. Why is that? You have to be a little careful here. The observer is at rest now, source is moving towards the observer, and the frequency now f naught is actually this f, because when these waves come towards the vehicle will receive the waves at a frequency f. That wave is only emitted from the vehicle again. So the frequency emitted from the vehicle will be f. So if you substitute those values, f dash equal to C over C minus V into F. I hope you understood that. Okay, careful. Now for the second case, the original frequency should be this F and the received frequency F. Okay, fine. Now what can I do? Instead of F, let's substitute this value. So F dash is going to be equal to C, C, never mind. No, C over C minus V into, ignore this part, instead of F, I'm going to substitute the other value. And what is that F? C plus V over C into F naught. Instead of F, I have substituted this value. Okay, what will happen to you? You can cancel out that C. Am I correct? This C and this C can be cancelled out, and finally I will get an equation F dash is equal to C plus V over C minus V. What is C plus V? What is V? V is the speed of vehicle. Speed of the vehicle, correct? Right. Now, if you take the speed gun has two frequencies at its around it. The one is F dash, the frequency of the reflected sound it has, and F naught is the original frequency of the sound emitted from the speed gun. So there will be a beat frequency, F beat, and that will be equal to F dash minus FO, because look at this value, F dash equal to C plus V over C minus V. C minus V is a smaller value, C plus V is a large value, and that is multiplied by F naught. So this value is actually greater than 1, so F dash will be definitely greater than F naught. Right, let's substitute the values. For F dash, I can substitute this value, that is C plus V over C minus V into F naught minus F naught. And finally, if you simplify this for F beat, you will end up in an equation. What is that equation? Final equation. Right, you can take C minus V as the subject. So when you take C minus V as a subject, C will get cancelled and you will end up in this equation, 2V F naught divided by C minus V. Okay, this is the final equation. Don't by heart this. If you can remember, there's no harm in it, but sometimes it will be difficult. Try to remember this. This equation is F dash. What is F dash? Equation, the apparent frequency of the reflected wave, frequency received by the source again. This equation. You just have to add the speed of the moving object and add it with the speed of sound in air. Then you have to subtract it from speed of sound in air and get the ratio and multiply by F naught. That is how it is. And this is the equation for the beat frequency. Okay. So in essay questions and all, sometimes we will have to derive these things. In MCQs, if you can remember this, it will be easier for you to handle the question, and you can save time as well. So this theory part, yeah, it's just manipulating the equation, substituting, understanding these things. Try to do it on your own and see if you're getting these answers. The next part under waves is Doppler's effect for light. Now we've been studying about Doppler's effect, but mainly for sound, but we can apply Doppler's effect for light as well. Let's see what's it all about. Now when it comes to light, this is the key word here, light. We know light is an electromagnetic wave. So it belongs to the electromagnetic spectrum. I hope you can remember electromagnetic spectrum from your O levels or from your basic chemistry. So let's have a small analysis about that. This is how the electromagnetic spectrum is arranged, and when you go from left to right in this series, we have arranged it based on frequency. So when you go from left to right, frequency actually increases, but wavelength decreases. That is how this spectrum is arranged. Okay, we will be studying about electromagnetic waves in the next lessons, but since we are talking about light, you need to know about this. And when it comes to the visible light range, there are 7 colors in visible light. Now this is what you see here is white light, but inside white light we have 7 colors, and how that in small classes we have learned these colors in rainbow. So we learned it as VIBGYO. So how do you place VIBGYO? I will teach you an easy method. Here we have violet, here we have red. So in VIBGYO we have 7 colors. V will be to the side of violet, R will be to the side of red. So when you write VIBGYO, you have to write like this, VIBGYO. Okay, from left to right, red, orange, yellow, green, blue, indigo, violet. These are the 7 colors when it comes to light. And you should understand, when you compare these 7 colors, when you go from left to right, the frequency increases and the wavelength reduces. So the 3 colors we are going to focus mainly are red, yellow and blue. Okay, so when you compare red, yellow and blue, we can compare their frequencies and their wavelength. Red will have a lower frequency but higher wavelength, and blue on the other hand will have high frequency but low wavelength. This is the order for those 3 main colors. Alright, now let us see how Doppler's effect works for light. Now assume there is a earth, because from earth only we are observing, right? We observe stars mainly. So earth is going to be our observing point. So you are the observer, you are on earth and you are observing a star mainly. Okay, so imagine you are on earth. So earth is like the observer. And there is a star. Okay, right, the star. Now there are certain stars which move towards earth and there are certain stars which move away from earth. Let's say there is a star which is not moving. Let's say it's relative to earth, it is at rest relative to earth. So from that star the light waves will approach earth. Okay, remember earth is the observer and the star is the source, correct? So let's say the star is emitting light and star is at rest. So if the star is at rest, observer is at rest, and you are on earth, with respect to earth you are also at rest. Let's assume like that, both are at rest. So there is no relative motion, there is no Doppler's effect, correct? So the star will be emitting light. The frequency of the light which is received by earth, let's say it is f0 the frequency, and the wavelength is lambda naught. Okay, right. When it comes to sound, we learnt about Doppler's effect. We compared the Doppler's effect based on the frequency, change in frequency. So this is the set of equations we studied. Okay, so it was completely based on frequency. But when it comes to sound, when it comes to light, we compare Doppler's effect based on wavelength. Now here there is no Doppler's effect. What's the reason? There is no relative motion between earth, that is the observer, and the star, that is the source. But sometimes the star might be moving towards earth. Okay, right. Then problem comes. So I will quickly consider 2 cases, where one where the star is moving towards earth, the other one where the star is moving away from earth. Right, like I said, 2 cases, and these are the frequencies and wavelengths received by earth, and these are the frequencies and wavelengths received by earth when the star is moving away, when the star is moving towards, and I have taken it as the speed of the star at which it moves with respect to earth. Okay, now when you have a look at this, we have already learned that when the source, star is the source, when the source moves towards the observer, frequency will increase and wavelength will reduce. Okay, so when you compare those two, here we will be getting f1 frequency will be greater than f0, and at the meantime lambda 1 will be less than lambda 0. Okay, if the frequency is increasing, wavelength should reduce. Similarly here also, here it will be the other way around. It will be the other way, right? Fine. So if this star appears to be in yellow color, when it doesn't move, okay, when it doesn't move, now the star moves, so the wavelength of the light received by earth is decreasing. So look at this, when you go from left to right, it means the wavelength decreases. So if the star is moving towards earth, the star will look blue in color, because blue has lower wavelength and higher frequency than this yellow. So we call this blue star, because the original color of it is not, it might not be blue, but since it is moving towards earth, the waves released from the star and the waves reaching earth will not be lambda naught anymore. It will change, it will appear to be in blue. And what will happen here then? The star is moving away, so the wavelength received by earth is less than its original wavelength. So this star will appear in red color. So there is no surprise, this is called a red star, or we call this phenomenon blue shift. We call this phenomenon red shift. That is another way you can okay, that is it. And then in addition to this, there is an equation. I don't think this is there in your syllabus, but in one of the years 2012 essay, they had given a comprehension question where they had given every detail, a paragraph, and then you have to read it and get the answer. So now there is a change in a wave in the wavelength, right? Here if you see there's a change in wavelength. So I can say delta lambda. What is delta lambda? In this case it is lambda naught minus lambda 1. That is the change in wavelength. And here the delta lambda can be written as delta 2 minus, it's not delta 1 here actually, I'm sorry, it should be delta naught, because we have to compare the wavelength with the original one. Okay, right. So here delta 2 will be greater than delta naught, so its change in wavelength is this. So there is an equation which connects these things, that is this, delta lambda over delta naught is equal to V over C. This is that equation. All right. The derivation and all are not that important. Try to remember this equation. Okay. Right. Now I know you are a bit confused. Let's see. Now delta lambda is the change in wavelength, which we call Doppler's shift. That's the name we give it. Okay. Delta lambda. And lambda naught is the original wavelength of light source. Delta naught. Lambda naught, and V is the speed of the light source, the star at which moving, and C is the speed of light. Earlier in our Doppler effect equation, C was speed of sound, but in this one we are talking for the Doppler effect for light, so C is going to be speed of light, that is in vacuum 3 into 10 to the power 8 meters per second, that one. I have defined the components here, right? Most probably they will give you this equation and they will describe these things, but it's safe to know these things. Okay, so this Doppler shift can take place when a star is either moving towards Earth or moving away from Earth. Not only that, it can happen when the star is rotating as well. Now imagine a situation like this. Imagine a star is rotating, so we have Earth and the star. So let's consider this situation where the star is rotating like this, that is anti-clockwise direction, correct? Okay, fine. Now if you take this point of the star, it is going this way because it is rotating that way. Yeah. So from here it is like moving towards Earth, right? Moving towards Earth. And then when you go to this point when you see this point, let's say this is the observer, okay? And this point of the star is appearing as if it's moving away from Earth, correct? Then compare this situation to these two situations, right? So what happens is, since this part is similar to this part, okay, star is not going towards Earth, but this part of the star is like moving to it. It appears as if it's moving towards Earth now. Now you can't compare this and this, because here the star is not rotating. Here the star is rotating. So this part of the star will emit wavelength, light with lower wavelength and high frequency, so that this part of the star will appear blue in color. Okay, and similarly you can compare this part of the star to this, because that part of the star is moving away, so that part of the star will appear red in color to Earth. But originally it's not that color. That is how it appears to us, since we are the observers in Earth. So this is another phenomenon which explains Doppler's shift. If not Doppler's effect for light, this also happens due to Doppler's effect of light. Sometimes in statement questions they will ask, is one of the following a phenomenon due to Doppler's effect? Then there will be a statement, stars moving towards Earth appearing blue in color. So yeah, that's correct. Stars moving away from Earth appearing red in color. Correct. Those are due to Doppler's effect. Not only sound, it can happen with light also. Two cases we have discussed, and this equation, I don't know how much it's important. They had given this equation in that essay question, but for your information, just try to remember this. Delta lambda is the difference in wavelength. Lambda naught is the original wavelength. V is the speed of this light source, the star in this case, and C is the speed of light.